Alright folks, welcome to part 7, the part that everyone was waiting for, where finally we have enough knowledge to look at the code of our deformer. So we're going to write our first assembly code. Correct? Everyone is happy? Yeah, let's get started, right? So first thing first, we are going to declare a code segment, right? And the code segment starts with .code and ends with end keyword, right? Really important. Then we are going to declare our function, right? So name of the function, procedure, name of the procedure, then the keyword proc. Then we are going to end that with name of the procedure and p, which stands for end proc, as we did in the dummy project. This here, nothing new. Now, we have 4 arguments. Where are those 4 arguments going? So we discussed that in the previous video, all right? But there are a couple of things that surprised me when I did that, right? Because I told you, all right, floating point going to XMM register, right? So first argument, you can see it here, is actually a double pointer because X is a double, so we grab an address to a double. It's a double pointer. You expect that to arrive into XMM, right? The first XMM, so XMM 0. Wrong, because it's a pointer. True, it points to double data, but the value itself is just an integer. It's an index into the massive array, which is the memory, of course. There's a massive simplification, but that's what it is. It's a pointer. And assembly doesn't care whatsoever if it's a pointer to a double, a pointer to an integer, a pointer to whatever. It's a pointer. It's an integer. So it's coming in into RCX. Same for the normals. It's coming in into RDX. Then the weight is actually a proper double value. And that's coming in into XMM2, right? And then finally, the point count is an integer, so it's R9. So really quickly, I'm going to repeat that. So the values comes in the argument. So RCX, RDX, R9, R8, R9, if they are integers. If they are floating point, it's coming in into XMM0. Next one, I'm just going to use M1. It's XMM1 just to save some typing, right? That's where they get in, right? So the first argument is here. Second argument is here. Third argument, fourth argument. Let's try to align that a little. All right. I'm wasting so much time with this stupid stuff, but all right. So the first argument is an integer, so it's RCX. Second argument is an integer, RDX. Third argument is a float, so it's an M2, XMM2. Fourth argument is an integer, so it's R9. That's how we are gonna get the argument. Now, let's talk quickly about an assembly instruction. It's composed of several parts, right? Based on instruction, the composition is different, but those are the rule of thumb. First, you have a mnemonic. Mnemonic, I don't know how to spell that, but let's call it mem, right? So it's a name which defines the instruction, what the instruction does. And it's a name which makes sense for the humans, not for the computer, right? So that's the mnemonic. Then we have the destination argument, operand, then the source, and then you might have other sometimes third parameter, right? And of course, destination and source might be different meaning as operands, but basically you get 2 operands. And usually the first one is the destination, the second the source. So let's have a look at the first instruction. The mnemonic is move st. Move stands for move, right? That's basically when you copy memory. You move memory from one place to another. SD stands for single, double. So double precision. S stands for single, right? So it means move, copy a double. We want to copy that double inside XMM6. And keyword PTR RCX is the source where we're going to copy the value from. It looks crazy, but I'm going to explain a little what it is, right? So in RCX, we have the value, which is the pointer in memory we want to read from, right? So in order to read from that memory location, there is a nice way to do it is you tell how much you want to copy, how much memory, and then between square brackets, the address. And it can be a register, or it can be, I think, an immediate value as well. I'm not entirely sure. But, so here we are saying, I want to copy a keyword, which stands for quad word. A word is 16-bit, so quad word means 64-bit. We are copying a double from the address defined in RCX. So basically means we are copying the first double in our point array. The second instruction is move single precision, right? So we are moving one float. Single precision means float, 32-bit, right? And that's why in the pointer, we are saying deep word, double word. So 16 times 2, 32-bit. And we are reading from the pointer stored in RDX, and we know that's the normal. We have it here, all right? Now, that's not the only way to write instruction. What we are writing here, I think, is the Intel signature. I don't know if signature is the right name, but basically it's how Intel convention, right? It's the Intel convention, because there is also another convention which is called AT&T one, which is slightly different. So you have the mnemonic first, then you have the register as swapped. You have the source and then the destination. And I also think you need to use percentage or dollar, I don't remember, to define a register, right? So it's slightly different. I think by default, for example, GDB on Linux shows you the AT&T convention, but you can change that. And I'm pretty sure that also GCC lets you compile with both, right? You just need to specify which one you're using and will work accordingly. So here we're using the Intel one. I think it's called Intel one. If it's not, sorry, I will figure out for the next video. So we load those two values into the register. So we have it there, we can use it. Before we can use it though, if you remember, XMM 7 holds our normal. The normal is a float. So we have a double and a float. We cannot operate with these together, right? Usually in C++, what happens is that there is an implicit conversion there. So in C++, the compiler defines a list, an order of data type, right? So I think the lowest is the integer, the highest is the 64 floating point value, so the double, right? So there is an order for that. I will try to find it. It's interesting. So basically, when you have mixed value, what it's going to do is going to raise the lowest value in this list to the highest. So let's say that, for example, this list is, I'm making one up, but just to give the point. So double float int bool, right? And it goes from right to left, right? So the lowest is bool, the highest is double. So if you have double times float, what it's going to do is convert the lowest, so float is the lowest, to the highest. So we are going to get this. Oops, double. And based on the compiler setting, you might get a warning or even nothing, right? So usually you get a warning when it's the opposite, when you're forcing a value from higher to lower. But that's what happened. And C++ does for us automatically. In assembly, you guessed it, there is no such thing, right? We need to do that ourselves. So we need to convert this float to a double. And that's exactly what the next instruction does. It looks like a mouthful, I know, right? CVT-SS2SD. But once you know what it means, it makes a lot of sense. CVT stands for convert. SS means single precision. 2 stands for TO, right? Kind of like a teenager speaks. And SD to single double. So this whole instruction means convert one float to one double. That's exactly what we need, right? And that's what we're going to do. Sorry. And the operand say, okay, grab the value. So store the value in XMM7 and grab the value from XMM7. So we are kind of reading and storing the same place. So it's an in-place operation we're doing right here, right? So now XMM7, right, actually has the normal value but as a 64-bit value. Awesome. Next, we want to scale our normal, correct? So we're going to scale by the weight value, and the weight value is into XMM2. So we're going to multiply single digit, what that the mnemonic means, right? And the two operands are going to be XMM7 and XMM2, and the result is going to be stored into XMM7. So now the final value in XMM7 is actually our normal scale. The last things we have to do is to sum, and that's what the next instruction does. Add single double, add the two value in XMM6 and XMM7, and store the value into XMM6. Perfect. We have our final X value for our point, correct? So what else we need to do? Oh, well, we need to write to memory the values in the register, right? We need to write to actual RAM so that Maya can use that value. So in the first instruction, we read from memory into a register. So you guessed it, we want to do the opposite. So the destination is going to be memory and the source is going to be the register, right? So we are moving a single double. So MMM word, we actually, if you hover this one, is MM word stands for quad word, double precision, 8 bytes or 64-bit. So it's the same exact thing to write keyword. It's up to you which one you want to write. I write differently so you actually see both. So we are copying 64-bit worth of data into the address, to the address defined in RCX, right? And the source of the data, so what we want to write, is stored into XMM6. So after this instruction is written down, awesome, our value is written in memory and we're good to go. All right, so then next we need to process Y and Z. We are going to do in the next video, right? And before doing that, in the next video, we are going to actually step line by line the assembly and see what is happening there. All right. So this is it for the first video. I hope you liked it. So see ya in the next video when we are going to finish up the explanation of this code and actually see step by step running. All right. See ya in the next video, guys.